All right, guys, so hello. So today we are going to be discussing molecular orbital theory. Now, molecular orbital theory, usually you would learn that after learning the VSEPR theory. And basically, the molecular orbital theory gives you a better understanding than VSEPR theory does. VSEPR theory can be confirmed given the molecular orbital theory. They both are very good to know when you're studying chemistry, and you usually will be required to know them. But the biggest difference that I would say is that the molecular orbital theory, there's an actual diagram that you can follow that works every single time. You can determine bond ordering from that. And, you know, you can sort of, without a shadow of a doubt, understand and know what that bond order actually is. Because if you're doing just the VSEPR theory, when you do your Lewis dot structures, which is part of VSEPR theory, a lot of times you can get it wrong. And you do have to check when you do your Lewis dot structures to make sure that it is the correct structure. And the way you would do that is by calculating these formal charges. Now, the formal charges is the charge of each atom in your molecule. And the way that you determine that, the way that you would determine that is you take your valence, your valence electron number, so the number of valence electrons for that particular atom. And from that, you would subtract your number of lone pairs, and you would subtract half of your bonding. Now, what do I mean by half of your bonding? Well, for example, let's say that you have dihydrogen. This is the Lewis dot structure because they each have only one electron they share. Now, normally we would talk about an octet rule and how they want to have that 8 valence electrons due to the noble gas because it's very stable. However, there are some that are different, like hydrogen and helium. They're entirely different. They do not need electrons all around them. They just need that too. So this is the Lewis dot structure. But how can we make sure that it is correct? Let's say you're not sure if you did it properly. Well, the way that you would do that is you would take your valence electron number and you would follow this whole little thing right here. Now, how would you do that? Okay, well, hydrogen, if you look at the periodic table, it has one valence electron. And I'm writing it as VE. Okay, well, how many lone pairs are around this hydrogen atom here? There are no lone pairs, okay? How many bonding are there? Well, there are 2 electrons right here, but they get equally dispersed between these 2 hydrogen atoms. So it's one hydrogen atom here and one electron, one electron here, one electron there. So half of this bonding would be 1. And that would give you your formal charge of 0. And it's the same for both of them because they both have the 1 valence electron and the 0 and the 1. Okay, but like let's say, what if this was a double bond here? What if there was a double bond? Well, it would be the same type of deal. It would be 1 valence electron minus 0 lone pairs minus, but now you would subtract 2 because you're getting 1 from each bond. And you don't have to think of it that way. The way you can think about it to make it easier for yourself would be, okay, well, is it a single bond? And if it's yes, then that would be number 1, But you should know all of this already. And if you don't, I can, of course, if people would like it, I could make a video discussing that. But that's the VSEPR theory. That's sort of how you tell from Lewis dot structures everything. But now we're going to talk about this thing called the molecular orbital theory and molecular orbital diagrams. Well, molecular orbital theory, I'll start drawing. It's quite simple once you get it. It takes a bit of practice. For me, I could not understand it the way that everybody else was explaining it. But then I saw one person explain it in this way on YouTube. I have not since been able to find their video. Actually, it wasn't on YouTube. It was on some site that they wanted me to sign up for momentarily. And I did because I was desperate. But I figured, not everybody wants to do that. So I might as well make the video here and make it more accessible. And plus, there's no reason for me to withhold information on how to do this. Like, yeah, it would be fun to make money off of it, but that's not fair to the students. I've been a student before. I know that it's not fair. All right, so we'll start with one that's without question. So F2. Now your Lewis dot structure, it would look like this, and there would be, the little lone pairs all around it. It would look like this, and it would have a bond order of 1 because there is one bond right here. Right, hold that thought. It is much easier, I think, and more absolute and understandable. Make sure you know it this way. Okay, so I'm going to share with you a periodic table real quick. All right, so we're doing F2. F2 is right here. So F2, it has 9 electrons on the periodic table. That's its atomic number, okay, but we have 2 fluorines. So that would mean 18 total electrons are present. Okay. So we have 18 electrons. Now, how do we fill this up? Well, if you remember from other sort of orbital diagrams you might have done, you do one spin up and then you do one spin down, sort of half arrow or L's, however you would like to think of it. So that's what we're going to do. We're going to fill this up. So that's 2, 4, 6, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18. That is it. So now to determine your bond order, you take your number of bonding minus number of non-bonding, divided by 2. And the way you can tell this is if there's an asterisk, that means that it's non-bonding. So let me just, I'm going to underline those that are non-bonding. Non-bonding, 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 non-bonding. The rest that are not underlined are bonding. So in this particular example, what you would do, like I said, is count up the number of bonding and non-bonding. So right here, we have the sigma 1s orbital. And also, the only thing you need to memorize as far as the molecular orbital diagram and things are just knowing, okay, well, there's one orbital and memorize this basically, this basic structure, this sigma star, and these 2 lines go here, 2 lines go here rather than one, the rest of them, that type of thing. Now we're going to count our bonding. So our bonding, okay? 2, 4, 6, 8, 10. So we're going to have 10 bonding minus our non-bonding. Right here we have 2, 4, we have 6, 8. Now, you might be wondering how you can double check. So the way you can double check is pretend, so like what if you were just adding these numbers instead of subtracting them? Well, that number, the sum of those two numbers would need to equal this, and they do. 10 plus 8 is 18. So 10 minus 8 is 2. Sorry. And divided by 2, that would mean 1. So it would be a bond order of 1. Now, the other thing you might be asked is this paramagnetic or diamagnetic? Now, the way that I can say this in the easiest sort of way possible. So, paramagnetic means that not all of them are paired up. So, diamagnetic means there is no charge. Paramagnetic means there is a charge associated with the molecule. Well, if you look at this original right here, there is no charge. It has a charge of 0. But the way you can tell through this diagram is all of these are paired up. There are spin ups and spin downs. There's nothing that is like unpaired. So if this were F2 with a negative charge, just hypothetically speaking for learning purposes right here, if this was negative, that would mean it wouldn't be 18, it would be 19. So there would be an extra 1 here. And in that case, F2 negative, difluoride negative, this would mean it is paramagnetic. However, this is not the case. They are all paired up, so this is diamagnetic. Okay, and the other thing is this little thing that would mean that it would be a single bond. All right, let's try another example just to drive this sort of home. Maybe if you don't quite understand what's going on, and I should not have erased that. Whoops. Hopefully with this next example, that clear the air. Although this next example is gonna it's not complicated, it's just not quite as straightforward as something that doesn't have a charge. But I promise you it's not scary. It's not terrible. Okay, so let's say we're gonna do lithium, dilithium, so there's 2 lithiums, okay? But it has a 1 positive charge. Well, let's say we're looking at this periodic table right here. Lithium has 3, so there's 2 lithiums associated. It's, diatomic right here. Lithium, so it would be 6 electrons. But if you remember, it has a 1 positive charge. So that means we need to, that means we need to subtract 1 electron. So if this was a neutral electron, atom or molecule, it would be 6, but we're subtracting 1 electron, give it that positive charge. So we actually have 5 electrons associated. This is actually quite easy to do. 2, 4, 5. Bond order. Okay, well, in this, it's going to be, 2, 3, minus 2. Divided by 2. And 3 plus 2 is 5, so we know that that is correct. That's going to equal 1 over 2. So that is the bond order for this molecule. Is this paramagnetic or diamagnetic? Well, look at this. We have these 2 that are paired, these 2 that are paired. This one is not paired. So therefore, it does have a charge associated, also seen here. So this is therefore paramagnetic. And one way you can sort of remember and distinct between para and diamagnetic is diamagnetism, um, meaning there is no charge, but this does have a charge. It's not completely filled. Okay. I hope this was useful. I hope you guys can use this in the future. Let me know if you would like more chemistry videos.